Good morning, everyone. On this occasion, I will present my research about energy conversion with Savonius Turbine. The title of our paper is Prediction of the Hydrodynamic Performance of an Elliptical-based Savonius turbine using Computational Fluid Dynamics. My name is Yusvika as the first author, and the others are Sutaji, Mr. Prabowo, and Mr. Syamsul Hadi as the corresponding author. Okay, let's start. List of content. First is research background. Second, introduction. Third, object and geometry. Fourth, simulation setup. Five, validation. And six, result and discussion. So, let's do the slide 3. Background research. The utilization of EBP or energy baru-terbarukan for electricity creation in 2018 was 8.8 gigawatt or 14% of the total power generation capacity of 64.5 gigawatt from fossil and non-fossil. From the value of 14% EBP, half was hydropower or about 4.4 gigawatt. This value was still far from the potential which reached 94.3 gigawatt. It's only 4.6% of the potential energy from hydropower. On the other hand, in 2018, the electricity production achieved 284 terawatt-hour, which most of the production was produced by coal around 56%. Besides, renewable energy source were about 17%. So, the question is why it could happen. Based on the analysis of the Ministry of ESDM, the low usage of EBP for electricity is due to the relatively high production price of power plants, making it difficult to compete with fossil plants, especially coal. Okay, next slide. The main driving force. Based on the data in 2018, the potential for renewable energy in Indonesia for hydropower was still very large. So, there were still many opportunities that can be exploited from hydropower source. Our research about Savonius turbine is one of the devices that can be applied to generate electricity. With suitable design, it is expected to increase electricity production in Indonesia. Next, the introduction. The basic principle of Savonius turbine is based on the drag force. It allows the turbine to move with rotating motion. The rotating speed is influenced by the effectiveness of the blade profile in capturing the kinetic energy contained in the water stream. The new elliptical profile will apply to our research. Then, compare power coefficient or CV value of the elliptical profile to the semicircular blades or conventional blades. Our research also have goals, advantages, and some limitations. First, the goal. Found the most appropriate blade profile according to the case of study. Then limitation. The research is conducted by simulation with the steady state approach. Then the data will only be sent to the coefficient of power. The third is advantage. The simulation results data can be a consideration for designing low capacity power plant using Savonius turbine. Next, research object. The current research object is how we can generate electricity by taking advantage of small canal water flow. Meanwhile, the converting device from water flow to rotating motion is adapted from Alon's research of Savonius wind turbine. This research was conducted using semicircular blade profile. With detailed geometry of the turbine is theta with 47.5 degrees. The length of M is 54% from AO. Sorry, 54% from AO, and the height is uh, 370. The diameter is 245, and the aspect ratio is 1.5, and we can see in the slide. On the above of the right slide, there is a Savonius setup. It's applied to the water channel, and the below pictures are 3D geometry of turbine with 2, 3, and 4 blades. Next, simulation setup. The pictures are simulation setup of our research. The simulations were carried out using ANSYS-CFX 19.0. It used sliding mesh and multiple reference frame technique to modeling the motion. With multiple reference frame technique, the domain is separated into two regions. We count as rotating domain and a fixed domain. The boundary condition with inlet velocity, and pressure outlet, and then the wall is not safe condition with the turbulent K omega SSD and the rotating domain with angular velocity. The solver setting we using at friction second, upwind, the turbulent numeric with high resolution, and the dynamic component mode using velocity and pressure coupling. The post processing will conducted by velocity contour and the torque. Then next, to validate the numerical setup and power value, we doing validation setup. With small error value, it indicates that our simulation can be carried valid. So, in this study, the role model of our geometry design and the performance value of the subversive turbine is validated with the numerical result by Patel et al. A conventional semicircular cut is performed, then torque values are compared to the torque values of this reference paper. All simulations are performed at constant water velocity for V, or the velocity by 0.6 meter per second. Based on the numerical setup that we have obtained, the performance and the torque error percentage are present in the table. With error less than 3%, we are able to achieve that the simulation results. Okay, next. In this slide, in this type of research, my study performed to achieve the optimum element of simulation. It will give more primacy, lower requirements of computability, and shorter time needed to complete the simulation. My study is done with adding the element of mesh in this regard. Understand the mesh size at the same boundary. Based on the table, mesh setting number 2 provides more optimal setup which perform minimum error value about 1.5%. So we have so in this section we will discuss about result and discussion. The Savonius turbine can operate due to the pressure drop and the lift force acting on the sub and the curve. The force can differ for every angle of attack, and each shape has its own force coefficient. Therefore, the moment pushes the blades to turn at a certain angle. It can happen because of the variation of the force during the device rotation. Based on the previous study, the high torque extracted by turbine is at the angle of attack 90 degrees, or when the flow perpendicular to the chord line of the bucket. The first result is about comparison of the power coefficient between semicircular and elliptical profile. This figure shows the comparison of the power coefficient that can be obtained by each blade type. For elliptical curve with no blades, the maximum power coefficient value, or CP, is 0.738 that can be achieved at tip speed ratio 1.0669. Besides, the semicircular blades can achieve the maximum power coefficient or CP value is about 0.513 at tip speed ratio approximately 1.2. Based on the graph, we can see that elliptical profile of turbine blades provide more high power coefficient compared to the conventional blades or semicircular blades. So next is the last result and discussion. The number of blades plays a critical role in the performance of the Savonius turbine. It also has unique behavior depending upon the operating condition. Increasing the number of blades can reduce the fluctuation of the dynamic and static moment of the Savonius rotor along the angular position of the advancing bucket. To understand the effect of the number of blades, we perform a numerical simulation with variation of blades number 2, 3, 4 blades are applied to our case study. This figure also shows the comparison of the power coefficient that can be obtained by each blade type. For elliptical profile with 3 blades, the maximum power coefficient value or CP is 0.337. It can be achieved at tip speed ratio about 1.069. Besides, the elliptical profile with 4 blades can achieve at maximum power coefficient 0.624 at tip speed ratio approximately 1.2. So, in the conclusion, the highest power coefficient is achieved by 2 blades turbine with elliptical profile. It can produce more coefficient to about 0.7 at TSR about 1.2. I think it's enough. Thank you very much for the attention. See you.